Hello. So, last time in our discussion of metric versus the imperial system, we talked about distance, and going to use that as a segue to go into mass, but we're going to take a side trip first, because with distance, well, not a 100% side trip. It'll make sense in time. So, distance is generally one-dimensional. We can do square feet and cubic feet. So that's where we're going to go first. Is we're going to go into the third dimension here. And so someone decided we'll take the cubic centimeter and we'll call that a milliliter. And then we will take 1 milliliter of water we'll call a gram. So we've gone from distance to let's say capacity, three-dimensional distance if you want, to mass. Now, as we take this journey, a few questions come up. This is one thing I never understood, when we learned this back in grade school, like third grade, I think it was. So, like I said, we got our basic unit of distance is the meter. But to go from meters into capacity, from distance to capacity, let's call it, instead of using the meter, we went down to the centimeter. And we took 1 cubic centimeter. Now, 1 cubic centimeter is a milliliter. It is not a liter. 1 liter is actually 1 cubic decimeter. And so a decimeter is 1/10 of a meter. Probably the only time you'll ever hear anyone refer to a decimeter is when they're saying that a liter is 1 cubic decimeter. Beyond that, we never use it. And then like I said, we go from there into the, one cubic milliliter, 1 cubic centimeter or 1 milliliter of water is a gram. Now we do this in the English system. An ounce of water is a ounce of weight. So we sort of do the same thing. The difference is weight and mass are not the same thing. Mass is the amount of, it's sometimes described as the amount of matter that's there. Sometimes you'll hear the amount of space something takes up. That sounds more like volume or capacity. But it's the amount of actual matter that is there. And it is constant throughout the universe. I'm so many kilograms here. Go to the moon, I'm the same number of kilograms. Go to Jupiter, I'm the same number of kilograms. Weight changes with gravity. So I'm about 190 pounds here. Go to the moon, I'm 1/8 as much. Go to Jupiter, I am, don't know how many, but yeah, I didn't look it up, but I know it's a lot more because Jupiter's bigger than the Earth. So weight changes, mass doesn't. But few things I got to question here is, first of all, is matter random or is mass random? We've gotten down to the meter is so many wavelengths of light, and therefore it is now an exact measurement. So mass, it's based on, we took our distance, we shrunk it down to centimeters, we cubed that, and then we took water, and we got mass. So we could say, oh, mass is a definite amount. Except for the fact of why are we using water? Water is very important to us on Earth. We would all die without it. To the rest of the universe, it's not that important. It's I believe I could be wrong on this one, but I think there's actually more ammonia in the solar system than there is water. It's one of the moons of Saturn or Jupiter has like more ammonia on it than the Earth has water. So an alien might look at this and say, why are they using water? Why aren't they using ammonia? Or why aren't they using hydrogen would be the natural thing to use because there's probably more hydrogen than anything else in the universe. But we chose water because we did it randomly, despite the fact that people want to say the metric system isn't random. We chose a random substance. Now then, the other thing I have, like I said, we took the meter, took 1/100th of the meter, a centimeter. We cubed that. We called that a milliliter. We didn't call it a liter. We called it a milliliter. So we find out what a liter is, and we go back up, and it is actually a cubic decimeter. And none of this has anything to do with the gram or the. Well, actually, 1 liter of water will be 1 kilogram. That's the one thing where things actually work out nicely. Now, the kilogram is the basic unit of mass for the metric system, which is another thing which threw me off. Why isn't the gram? A kilogram is 1,000 grams by definition. That's kilo means 1,000. So why did we create the gram, then turn around and say, and a kilogram is going to be the basic unit? Here's the gram, 1,000 of these is our basic unit. Why didn't we just make the gram the basic unit? I never understood that growing up. I still don't understand that. We just sort of started randomly doing stuff. So why not a cubic meter will be a liter, and then a cubic liter of water because, again, it's important to us on Earth, so I'll say we'll do with water, will be the gram. And then we can work from there. And people would say, well, we'd have to start, day-to-day use. If we did it that way, then we'd have things like, we'd be weighing things in centigrams and stuff like that. But we do that anyway. We don't always use our basic unit of measurement. We use these, throw on these suffixes to define them as a fraction of the actual unit. So why not just say a cubic meter is the liter, a liter of water is a kilogram? That would make more sense. As a kid growing up, it would have made more sense. As an adult, I still haven't seen a reason why we don't do it that way. But because, science is science and it does what it wants, someone decided to do it the other way. Now then, now that we've gotten into mass somewhat, we can look at the English or the Imperial measure of mass. And a lot of places will say they'll give a weight, a pound equivalent, basically. It's here on Earth, 2.2 pounds is 1 kilogram. Or, a kilogram will weigh 2.2 pounds on most places on Earth, I should say, because there are actually measurable differences. If you go to the top of Mount Everest, then there will be it'll be a very small fraction of a percent, but it will still be a measurable distance or measurable difference from the weight. So take our kilogram to sea level, we weigh it, we take it up to Mount Everest, we weigh it again. It's going to be a very small bit lighter because you're farther from the center of the Earth, gravity's not affecting it as much. So, but people will still refer to mass in pounds in the Imperial, just because for most places, the difference on Earth isn't much different. And if we ever go to another planet, we're not going to use pounds. We're going to use, to get there, we use metrics to do all our measurements, so we're going to do everything in kilograms. Now, we do kilograms for weight as well. Go to Europe, go to the supermarket, look in the produce section, and you'll be buying things by the kilogram and not by the pound. So, to some extent, we treat kilograms as a unit of weight as well as a unit of mass because, again, here on Earth, unless you go to very extreme locations, it's pretty much the same thing. Now, there is an actual imperial unit of mass, which is not based on kilogram or not based on weight. The slug, and it is one slug is about 14.6 kilograms, so it's a big unit. The slug is defined as the mass that would be accelerated by 1 foot per second squared if a force of 1 pound was applied to it. Because again, while we do sometimes refer to pounds, we sometimes refer to our mass in pounds when we're doing the imperial. Pounds is actually a unit of force, or it could be looked at as a unit of force. So we apply this force to one slug of material and it will accelerate to 1 foot per second squared. And again, it's a large amount. It's an amount we aren't going to use that often, probably, but at the same time, one, we use all our basic units to make it. We didn't do 1 microsecond or one inch per second squared or anything like that. We used our common foot, our basic unit of distance, our basic unit of weight, our basic unit of time. So we aren't playing this whole, well, we're going to suddenly start measuring things in centimeters and start measuring other things in kilograms and stuff like that. And back to what I said about, I nearly forgot, I was going to mention this. The whole idea of let's make the kilogram one, or let's base our unit of measurement on the meter squared or the meter cubed. So a liter would be 1 meter cubed instead of one decimeter cubed, and go into stuff like that. It sounds weird now because when would we ever want a cubic meter of anything? However, back when we were inventing the metric system and doing all this stuff, we were still shipping stuff by boats and had large cargo containers and stuff like that, and a cubic meter as a unit of capacity would have been a perfectly legitimate. No one would have questioned as much. It would have been bigger than most barrels, but okay, so a barrel is now a quarter of a liter as opposed to 500 liters, or we wouldn't be doing these weird math games or whatever. It would have made sense to have our liter be 1 cubic meter instead of 1 cubic decimeter back at the time when we created the metric system. And so again, a slug would have. It's a large unit. It's what did I say, about 14.6 kilograms, which again, that's about 33 pounds. Back in the days of shipping things by ship, and 33 pounds as a common unit of weight for shipping something would have made sense. So measuring stuff in slugs, which again we didn't use slugs that often, but someone came up with the concept of the slug. It would have made sense for the time that we were doing all this. Now then, there's a guy. He was the Count of Quarina and Cerreto, and so he was titled man in Italy, and he is better known by his full name. Well, his full name was Lorenzo Romano Amedio Carlo Avogadro, and in science class you will only hear Avogadro used. And Avogadro did a lot of stuff with gases and measuring gases and the masses of gases. And he discovered that what we call Avogadro's number, it is the number, it's a mole. It's a new unit. It measures the amount of something there is, and not in the same sense as mass. This is actually the number of things. And basically, this is the number of atoms or the number of molecules, or instead of saying we have so many pounds or so many kilograms of something, we can count the exact number of molecules. Or that's what Avogadro's number is. And it is 6.022140076 times 10 to the 23rd. Or, say, 602 with 21 zeros after it. And I bring this up because among the various definitions you will find of the mole or the Avogadro's number, you will see reference to this is the number of hydrogen atoms in 1 gram of hydrogen. And again, why am I saying this? Well, because we gave, the wavelength of light is so many, or 1 meter is so many wavelengths of this kind of light. And 1 second is so many vibrations of cesium 137, I believe it was. So we can now say 1 kilogram, or 1 gram, or multiply by 1,000 with 1 kilogram is 6.02 times 10 to the 20. Again, if we're going to go with kilograms, it'll be 10 to the 26th hydrogen atoms. But we don't do this. You look up, what is the standard, what is the kilogram based on, or anything like that. You look it up, and everyone will say, most sites will say, oh, it's a random thing, and it is measured. We still have this, I believe it's a platinum cylinder, which is the standard kilogram. And if we wanted to compare kilograms, then we, take our kilogram to the Bureau of Science over in Paris, and we compare it and make sure, yes, the kilogram we're using is equal to this, and probably a lot of permits to fill out to do this. And no one will say, oh, a kilogram is so many atoms of hydrogen. And, we don't want to sit around and count hydrogen, so that would be impractical. Well, is it any more impractical than counting wavelengths of light or counting vibrations of atoms or anything? But we don't say this. We don't. No one says, oh, the official definition of a kilogram is so many atoms of hydrogen. It would make sense. But we don't do that for some reason. So the kilogram is still considered to be, by scientists, a randomly selected thing. And while, like I said, as I showed earlier, the second and the meter were also randomly selected, and then we turned around and we compared them to other things, and so now they are quote-unquote specifically defined, why don't we do the same thing with the kilogram? And my answer is, I don't know, and it's the sort of thing you look it up and no one else seems to care. So, we're going back to which is better, the imperial or the metric. Again, we don't use mass in the imperial, other than we don't use it in the same way we do for science, or we do with the metric. Basically, we use weight instead of mass because for day-to-day use, which the imperial is still good for, we do things in weight more often than mass. Where if we want to, if we start talking about volumes of stuff or capacity of so many cubic meters, so many whatever, then we recognize that different objects have different densities. So doing things by volume, the space it takes up, if you want to put it that way, we don't care so much about. We recognize here on Earth, weight and mass are almost equivalent depending on where you are. Sea level, it's almost equal everywhere. So why not just do weight? So that's it. Like I said, doing things using kilograms and grams and stuff like that. It is useful for science again because we got the whole multiplying by 10, and it's easier than 16 ounces to a pound. But at the same time, there is a lot of randomness, especially with mass, a lot of randomness went into how are we going to do things. Are we going to just do, a cubic meter, or are we going to do a cubic decimeter, and then we're going to apply it to water because that's a randomly chosen. It's an important substance, but it's still randomly chosen. That's it. Be massive and good day.